Okay, so it's a good time to get started. Let me go back to the previous example that we worked on, right? Last time we only have the last 10 minutes, and in those 10 minutes, we filled up the whole page, right? So I think that it is effective. It's desirable for us to go back to that page and discuss what goes on. Let me share that with you. Okay, so this is remember, or let me go back here a little bit. We are already moved on to module 6 about lean operations, and the goal of lean is to eliminate the waste, right? But to eliminate the waste, we have to know the waste, to identify the waste. So there are two perspectives for us to identify the waste. The perspective is waste of time at a resource. So we look at each of the resources that we have in our process, right? And see when the resource is productive and when it is not productive. And the second perspective, or the second focus, is we track one unit from the beginning to the end of the process, and ask ourselves along that time when the product is effective or productive, and when it is not productive, right? Okay, so we are talking about the waste of time at the resource, right? That's the first perspective for us to identify the waste. And for that, we worked on that example, right? So a machine is available for 24 hours a day. And in one day, the machine has to work on 5 jobs, 10 jobs. And so out of the 10 jobs, 5 are good jobs and 5 are jobs with rework, right? So the 5 good jobs means that we nail it in the first attempt. We don't have to do anything further because the outcome is good already, right? So for that, we call it as a 5 good jobs. The 5 rework jobs are different because in the first attempt, we fail it in some way. The outcome is not as we want it to be, right? So that's why we have to do it the second time. So that's the 5 jobs with rework, okay? So now let's look at the tree. We have the total available time. We just convert the 24 hours into the minutes, right? So we have these minutes. And next, we break the total available time into 3 categories: value at a time, non-value at a time, and the waste time. The value at a time is what? The time that we produce we create some features. Those features will be built in the product. The product will be sold to the customer, and then the features will be valued by the customers at the end, right? So we call that as processing time or processing activities. For example, you cut something, you drill a hole inside the metal, or we weld the 2 pieces of metals together, right? That would be the shape of the door or the seat or something like that. So all of those will be visualized will be viewed by the customers, right? And then they will value that kind of activities. So that's why we call it as value added, because at the end the customer will see that, will value it, right? They might see something good, they might see something wrong. So it is valued by the customers, evaluated by the customers at the end. So first of all, we talk about the processing time of the 5 good jobs. It takes 40 minutes to do processing, and because there are 5 jobs, so we multiply the 200 minutes, right? So that's a value at a time, the first component of the value at a time. The second component is the processing time of the 5 rework jobs. But remember, we fail in the first attempt, so we only list the second attempt here, right? Only the second attempt is included in the value at a time. So 5 jobs, 4 minutes each. We just multiply them. There are 200 minutes, right? So in total, the value at a time is 200 plus another 200. Okay. The non-value added time is for, in this particular case, is for the setup, right? Why it is called non-value added? The setup is necessary for production, but at the end, how we set it up is not valued by the customer. So it is necessary, but not valued. Then we call it as a non-value added time, right? So there are two components here. The setup time of the 5 good jobs. So 5 jobs, 20 minutes each, and we have 100 minutes, right? And the setup time of the 5 rework jobs, 5 jobs, 20 minutes each, and so we have 100 minutes. But remember, when we talk about the setup time of the 5 rework jobs, it has to be the second attempt, right? We fail in the first attempt. So no matter how we set up in the first attempt, right? At the end, the outcome is wrong. We just gotta throw that attempt away, right? So that's why in the non-value added time, we only list a second attempt. The first attempt is a failure. It's not necessary to have a failure. So that's why that first attempt setup doesn't belong to the non-value added, right? It has to be necessary. And second, it's not value. If it is value, it's already listed in the value added time, right? I hope you see the difference between the value added and the non-value added, right? So, and then we just add these two up, and then we have 200 minutes in total, non-value added time, right? All right, so the remaining not belonging to value added time and non-value added time will be belonging to the waste time, right? So the waste is the total available time, subtract the other two. So the total waste time is 840 minutes in this example. Okay, so after that, now the processing time of the 5 rework jobs in the first attempt. Again, we call that as a wasted work because we worked on it, but at the end, it doesn't bear the desirable outcome, right? So that work is wasted, and we should list that in the waste time. 5 processing times or 5 processing attempts, they are wasted. 5 times 40, they are 200 minutes. And then for the setup time, we also set it up 5 times, and they at the end they are wasted. So we multiply 20 with 5, right? So we have 100 minutes here. And finally, the idle time, right? The idle time is when the machine doesn't work at all. So we just subtract. We take 840, subtract 200, subtract another 100. Then the idle time is 540 minutes, right? So in the waste time, we have the wasted work. And we also have the time where the machine doesn't do anything at all. All right, so with these, we already complete the tree, right? And at the end, we come up with a new concept called the overall equipment effectiveness, or OEE, right? So the equation is we take value added time divided by the total available time. And at the end, the answer is 27.8%, right? What is that 27.8%? Let's call that as 28% to make it easy. It means that we invest $100,000, for example, on the machine. Then only 28% of that investment, or $28,000 out of $100,000, help us to produce the units. That will help us to generate the revenue. Okay, so only 28% of our investment directly help us to generate our revenue and profits, right? The remaining, they don't. The remaining times here, it doesn't help us to generate the revenues. Of course, you might say that the non-value added time is necessary, without the non-value-added time, we cannot produce a unit. That is correct, but we can reduce it, right? For example, in woodworking, sometimes the workers will build for themselves the rig, the drill rig, or some kind of rig, or jig, something like that. The jig will help them to set up the parts very quickly. And then they drill the holes, they put the things together very fast, right? If we do it like that, then we can cut down the non-value-added time. And then if we can retrain the workers, then we can also cut down the wasted work time, right? How about the idle time? How can we cut it down? For example, if you can promote your business, then we can cut out the idle time, and then we can cut out the idle time by cut out the wasted work time. We can cut out the non-value-added time. So now we will have much more time for the value-added activities, right? By doing that, we're going to generate much more revenue than before. The process will be more efficient than before, right? So the idea here is we look at our process, try to cut down the non-value-added time and waste time so that we can improve the OEE of the equipment, right, of our investment. Right, so I hope that you should be ready with this question. That will be question 24 in our homework 3, right? So by now, we already covered question 21, 22, 23, and 24 of homework 3. 22 and 23 for the control charts, right? I did not have a chance to show you directly during the class time like this, but at least I already made the videos, and I hope that the videos will help you to kind of learn how to draw the control charts. And last time we spent a good amount of time on discussing on how to interpret the charts, right? I hope you clearly see the concept and the reasons why we have to learn about the control charts. Let me share with you the canvas a little bit. Okay, thank you, Alida. Thank you for the feedback. All right, so let me click on let me share with you the canvas site. And I want to show you that the link for the homework 3 submission is already there. So when you click on Canvas, right, click on assignments. And then sometime by default, they show by date. I recommend you to show it by type, because by showing by type, we have homework 1 clearly as one piece, right? Homework 2, homework 3 as another piece, the project itself as another piece, the midterm exam as another piece. And then you can drop it out to see more details in it, right? Homework 3 part 1, again, this is only the information for you to go on Connect and do everything for part 1 on Connect, right? So let me remind you that part 1 is due next Monday, right? So that's part 1. Homework 3 part 1 is due next Monday. And for homework 3 part 2, we already covered the first 4 questions. So if you click on that link, there's no submission, right? So you should click on the second link, the link right here, where you would upload question 21, 22, 23, and 24. And it is due on Friday, November the 19th. Okay, so I try to space out the workload a little bit so that you would have enough time to complete the task. By the way, there are question 25 and 20 and 26, right? Homework 3, we're going to learn more, and then I will post the link for those 2 questions later. Okay, so they will be submitted separate from these 4 questions. Again, I try to space out the workload. Otherwise, a lot of things will be due at the same time. Then maybe it's not good for you to learn. It's all about learning, right? If it is too much at the same time, then we learn less than if we can space it out a little bit. Okay, so that's the homework 3 submission. I hope you're good. The project, remember, the checkpoint is due tonight, right? Basically, the first three parts should be done in the checkpoint. At the end, if you have some more question about the project checkpoint, please stay back with me. Otherwise, I will have my office hours at 3, right? In case you have further questions about the checkpoint. All right, so let me go back to the materials that we have. We are still at module 6 about lean operations, and we're done with the first perspective, right? And now let's talk about the second perspective, where we would find the waste. We will need to find the waste before we can eliminate the waste, right? So how to find it is an important question. So in the second perspective, we're gonna look at the waste of time of a flow unit. So let me share with you the PowerPoint for it. In the stamping operations of an automotive supplier, a piece of sheet metal has a flow time of little over 8 hours. The time in the stamping operation is spent as follows, right? And then they give us a long list of things that the piece of metal will have to go through. I would like to go back to the very first sentence here, and I would like to explain what is going on, okay? Why do we say stamping operations of an automotive supplier? If you look at a modern car factory like Ford or GM or something like that, then they have the assembly line, and we call that as the car factory, right? But you know what? Most of the parts that they use are not produced by them. It is by the suppliers or the vendors, right? So here we call it as an automotive supplier because they will draw the parts from the vendors, not produced by them. All right. So normally the setup is we have the big factory in the middle of this, and we have satellite vendors around the factory nearby. Okay, the satellite vendors are nearby so that they can quickly supply what the factory needs. And the vendors are separate. They are owned by other companies, right? All right. So we call all those as automotive suppliers. They provide the doors. They provide the dash panels with a lot of the electronics things that separate from the factory. And second, what is a stamping operation? Why do we need stamping in car manufacturing? So if you look at your own car, right, a lot of things is started as a flat piece of panel like this. Okay, it's just a flat piece of metal. I'm sorry, a flat piece of metal. So it's a little bit amazing, right? It's amazing to see that our car start with a piece of metal, because they will need to do the stamping to make the shape of the door, make the shape of the frames, and then later on the weld different parts of the frames together as a frame that we see in our car. And then they make the trunk, they make the hood, things like that, right? All starts out as a flat piece of metal. I watched the video. It's a very big machine. They will do it as a die. Die is the shape of the door, or the die is the shape of the hood, right? And then they use a die and press very hard, right, with a strong, very immense pressure on the piece of metal. And then that's how they shape the different parts of the car. And then, of course, later on, they put different parts together to have the cars that we drive, right? The VIN number, the part number, what they put on they stamp on the parts, but the stamping itself, right, is a whole door, the whole piece of the frame of this. It's a big piece of things. Yeah, that's right. Yeah. I encourage you, if you have time, just go onto YouTube, search for car manufacturing activities, you're gonna see stamping is a very important activity in the whole process, right? But again, the stamping happens in the vendors or the suppliers facility, okay? So that's why that is a context. I try to bring some story here for you to understand more about the real life operations in car manufacturing. I encourage you to watch some videos about it. It's amazing, okay? Because the machines are big, things are kind of high tech. They do have to do a lot of high tech things before they can do something like that. When a car is designed, you know what? They do not use a stamping. They use a hammer like this. They beat it. Okay, that's a little bit old technology. They beat the shape into the shape of the doors, things like that, right? Nowadays we do it in a higher tech. But so that's a stamping, right? So in this case, we track a piece of metal from start to finish, and observe when it is under operation or productive operation, and when it is not productive. Okay, so that's the point of this example. The time in the stamping operation is spent as follows: 3 hours waiting in front of the stamping machine. By the way, I appreciate your share, Theo, and also Christopher. So the time in the stamping operation is spent as follows: 3 hours waiting in front of the stamping machine for the batch to start, 1 hour waiting for the setup for the machine, 1 hour waiting for the other pieces of the batch to go through stamping, and only 1 minute of the stamping machine, and then 3 hours waiting for the shipment, right? So what is the value-added percentage of the flow time? So that's the question here. Under the whole lengthy process, which one is value-added? And for that, we calculate the value-added percentage of the flow time. So let me go back to the whiteboard, and I'd like to draw something so that we can see more details here. I believe that all of you already did this when you do the connecting, right? But just another chance for us to review the concepts. So we have module 6 about lean operation. Earlier, we already talked about the waste of time of a flow unit. Now we talk about the waste of time. Oh, I'm sorry, last time is a waste of time of a resource. And today we talk about the waste of time of a flow unit. All right. To do that, we are looking at the example of stamping operations. This is module 6, slide, I think, 23, right? So again, it means that we track a piece of metal from start to end, like this. So this is our stamping operation. It is a process like this. It doesn't mean that it's only stamping. It means other activities in the whole process, right? So the piece of metal will start here, and at the end, the piece of metal will be in the shape that we want, and it will be shipped out to the factory, right? The car assembly factory. All right. So if we track the piece of metal, then first of all, it stay for 3 hours of wait right here. Right. That's the 3 hours waiting in front of the stamping machine for the batch to start. So even the batch has not started yet. And then 1 hour waiting for the setup of the machine. right? They have to do the setup before the setup here might be they have to change the die. The die is a very big piece of metal like this. And then they have to use a crane to change from one die to the next die, okay? And then 1 hour waiting for the other pieces of the batch to go through. So 1 hour waiting. It's like we stay in line, we have to wait for the people to take their turns before we can take our turn, right? So the piece of metal will have to wait another hour before it can go through the machine. So actually the time is only 1 minute, right? 1 minute, value at a time. The flat piece of metal will be standing to the door, for example, and then we buy the car, we see that, oh, that's a door right there, because we have that 1 minute value at a time, right? And then even if the door is done, but then you still have to wait for another 3 hours to be shipped out to the factory. Right? So in this process, we see a lot of wait time. And the question asks us for the value added percentage. Or VAP. It is value added time divided by the flow time. The flow time is from the start to the end. The time it takes for the unit to go through. So let's put the number in. The value added time, remember, is only 1 minute. And the flow time is the following. So let's look at the whole process, right? We need to convert everything to the minute so that we can compare the numerator and the denominator. So in the denominator, we do 60 minutes times 3 hours, right? And then 60 minutes. Oh, I'm sorry. This is not multiplication. It is addition. 60 minutes. Another 60 minutes of wait. And then here is sometimes we miss. This is a value at a time. It is small, but it is part of the flow time. So we have to add it in, right? And then finally, with the 3 hours wait, so we do 60 times 3. Everything here is in minutes. So just imagine, we take 1 minute divided by 481 minutes, right? 8 hours, it's about 480 minutes, but then we still have the 1 minute value at a time. So we add everything up, we have 481 minutes, right? So the answer here is the following 0.00. It is a very small number, if you can imagine, right? Because we take 1 divided by 481. So it is 0.00208. Or in other words, we talk about 0.208%, right? It's quite shocking. At the end of the day, we calculate this and we see that the flow unit is only under activity, value-added activity in about even way less than 1% of the time, right? As a manager, when we look at this, we're not happy at all. It is way less than 1%. So we review our process, and we think that some of us might think that, oh, it's our very standard. It has to, the units have to wait before it can go through this or that, right? But as a manager, if you think hard, you might find a way to make it more efficient at this. And that's why Ford invented the assembly line in the 1930s, something like that, right? So just look at the assembly line of a car factory. The conveyor belt is at the top like this. And then there are giant hooks is hung underneath it where we put the cars in, right? So the cars are hung in underneath the conveyor belt, and the cars are moving slowly along the assembly line. Sometimes the cars are moved slow enough for the workers to walk with the car, to put in the mirrors, for example. If it is not that hard, the worker can even walk with the cars and work on the cars, right? By doing that, we can cut down the wait time a lot. Here we talk about many multiple activities along the assembly line. So if we can cut down the wait time at each of the activity, then we already cut out a lot of wait time during the production process. So in the assembly line, like a modern car factory, right? Then we would see a very high value added percentage because they already try hard to cut down the wait time. Right. So that's the second perspective. We track down one flow unit from the beginning to the end and calculate the value added percentage. And as a manager, right, you always have to think about how to increase the value added percentage so that we can cut down the waste of the during the production process. This about the car manufacturing context, right? But it can be applied to services too. As long as you think hard about it, you might find a good way to increase the value added percentage, right? Like Ford did in the last century. Okay, now we are just using that invention. All right, so that's the waste of time of a flow unit. So next, we would need to move on to the next big topic of Module 6, and that's about the Toyota production system, right? Some of you might ask the question, why do we have to talk about Toyota? It's just simply because they are the pioneer in lean operations, also in the quality revolution too. Then because of that, a lot of the things that we do today, we learn from the Toyota experience, right? We learn from their best practices. And you know what? Not only the car manufacturers learn from them, other companies in the services industry also learn from the Toyota production system, right? If you are in the hotel industry or the restaurant industry, right, you also want to learn from the Toyota production system. Of course, companies are different. When we learn the key concept from Toyota, we also add the things that is pertaining to our company, to our industry, right? All right, so the first thing that we can talk about the Toyota production system is a summary by Lycos. So this is a 4Ps model about Toyota. The first P is about philosophy, right? Long-term focus on quality and capabilities, right? So the quality here will need to meet the customer expectation, and then we would have high capabilities to meet with our own design specification, right? So that's the first P is about meeting the customer expectation and conform to our design specification. And to do that, we focus on the processes, right? To match supply with demand and to smooth out the flow rate of our production. Right? So that's the second. The third P is about people and partners. And the key word here is about respectful interaction, right? So as colleagues, we should respect each other. That's a social norm, right? But beside that, there's something else very important. If you are the manager and you are the boss, if you know how to respect your workers, create an effective partnership with them, then you can solicit ideas, information from the workers. And you know what? The workers, sometimes they know more than you because they are the workers that work with the cars. they see the discrepancies, they see the problems or potential problems, right? Then they know more than us. If we are the managers, we stay more at our desk. Then we will not know the details that the workers know. So the respectful interaction is not about the socialization, about the social norm, but it's also about the knowledge and the opinions or the ideas on how to improve the process to be better and better over time, right? So the third P here is very important. They stress that, they emphasize that for that reason, right? For the effectiveness of how to improve the process. All right, so the 4P here is about problem solving, ongoing improvement at the front line. Again, we have to talk about the front line because the workers know the details more than us, right? So, an ongoing improvement means that if we see a small problem, we try to fix it right away. We see another small problem, we fix it right away. So we fix it along every day, not just a big improvement project, right? We just do it bit by bit, and then we can make the process much better over time. Okay, so that's the summary by Lycus. Okay, and to be more concrete, normally they will talk about the TPS house. It's just a visual of the key things that Toyota does, right? So it looks like a house like this. At the top, we have the roof. The goal of the system, right? So in this case, we try to match supply and demand, right? To do that, we have to have the two support columns, or the two walls of the house, just in time and built-in quality, right? So they are the two pillars of the house. Just in time means that literally, right? If you need the door to put on that car, then the vendors will bring the door right when you need it. They should not bring it in earlier. For example, 1 hour earlier, right? It sounds good, but then how to where's that door? You have to build another room for the door. That's a waste of money, right? So just in time means that you're gonna bring the door right when you need it, and actually they can achieve it. Not exact time, but just a little bit before you need it, they already bring the door, okay? And then you have the door and put it in the car. That's it, right? So that's in time. And of course, you don't want to bring the door late. That will slow down our production process, right? So that's the first pillar, the main idea of the first pillar. Just in time or just enough. If we need this much, this quantity, then the vendors only bring that quantity in, right? The second column is about built-in quality, but it's not about efficiency anymore. It is about built-in quality. Um, uh, so in just in time, to be just enough, you would look at the demand rate and follow the demand rate to configure your production, right? Then in the built-in quality, they will focus on the defects. In an ideal world, if we do not have any defects, then we have perfect product, right? But of course, in the reality, we cannot get rid of the defects altogether. So the idea here is we try to reduce the defects by addressing the defects now and avoid the defects in the future, so that we don't have to have those defects anymore, right? So just in time and built-in quality are the two pillars of the house. And here are some of the details. To do just in time, at Toyota, they'll do more of the pull system. I'll talk about that. They'll do piece by piece or single unit flow, right? In other words, we talk about car by car here, right? If you do multiple cars at the same time, then you're gonna, in a sense, you do batching, right? When you do batching, you have some inventory waiting for one unit to be finished before you can process the next unit. And inventory is one form of waste because we lock up our time and money in that piece, in the inventory, right? So that's in the Toyota production system. They try to do piece by piece or car by car. So that station only needs to work on a car at a time, right? There's no more inventory going on. Okay. The U layout is another important concept. I will talk about that. The tech time is a new concept. We also have to learn that too. I would like to talk about the mix model and the fast changeover here. So in a modern car factory, right, they do not produce only one car model. Normally they build multiple models on the same assembly line. Okay. Why is that? Because if we only produce one car model, then the demand for that one car model just fluctuates every day like this, right? It means that sometimes the workers work a lot. Sometimes the workers will stay idle. They don't have to work on anything. That's not good, right? We see waste right there if the workers do not work anything. So if we mix the different models on the same assembly line, then now we can even out the workload for the workers, right? Because the demands of different models are different. So we can even out the workload for the workers, for the tools and equipment, right? To improve the effectiveness of our resources. So that's the reason why they do mixed model. But to do that, then technically we have to have the so-called fast changer capability, right? So earlier we worked on a car. We use this bit to turn the spools to put the parts together, right? But when another car comes up, you might need to use another bit, another size of the bit, right? So the fast changeover, for example, in many uh, processes, they use a barrel. When the barrel turns, then you have another bit ready to use to put another bolts or another screw of different size, right? Different size. But because you already have another bit, then you can work on that right away, right? So the fast changeover capability is another thing that important for the mixed model manufacturing. All right, so built-in quality. Then here are some of the details. Detect, stop, and alert. Right? We have to have that system so that we can detect the defects, fix it right away before we deliver the final products to the customers. We have to have the stop the light capability. Otherwise, how can you fix it, right? Not only this for this unit, but also for other units. Line up before the current unit, and alert the engineers, the chief engineers, to do something about the problem. Right? To do the detect, you have to do inspection. And how do we do inspection? In the ideal world, we might think that, oh, in that case, we put an inspection station at the end of each step, right? But then if there are thousands of stations, then we do then we do thousands of inspection. Is that good? That might not be good because too much inspection will slow the production down. It's not good, right? So as a manager, we think hard about inspection, and possibly we are very selective in putting out the inspection stations so that we can check other steps, but at the same time we can check the crucial steps right away. Right, the step is so crucial that if it is wrong, everything else will be wrong. And normally we put the inspection station after the activity that is more prone to error or defects, right? Then it makes sense to do it like that. Otherwise, we're going to slow down the whole process, and then it costs more to hire more workers and have more tools and equipment, right? So stop the line is another important concept. We have to configure the process so that we can stop the line in some way. I bet you already read that in the textbook. If we have time, I will talk about that. Stop the line. Six Sigma, right, is a strive for near zero defects. So out of 1 million units, right, we only have very few defects. So that's a goal, that's the ambition. But to do that, then we have to invest in our process so that we have high process capability, right? It means that the units will stay within the design specification most of the time. Nearly all of the units will stay inside the specification, right? So that we have the high sigma level, like 5.0 sigma or 6.0 sigma level, right? Control charts is for to monitor the process to find out if there are some abnormal impact of some factors, right, on our production process, and then we can get rid of the impacts by dealing with the sources of the impacts, right? So those are the 2 pillars, and then there are 2 foundations of the house: process improvement and stable processes. Process improvement. Okay, there's a Japanese keyword here called Kaizen. Kaizen means that every day we solve a little problem. We improve, we fix it, and improve and make the process better to deal with that smaller problem or avoid that smaller problem over time, right? So Kaizen is got a incremental and ongoing and little improvements bit by bit. Okay, that's the concept of Kaizen. And to do that, then the workers know best, right? Because they work with the cars, they are the front line, they knows what is going on better than the managers. So the workers will lead the problem solving and process improvement, right? And again, the implication is if you are the manager, then you need to you should find a way to mingle with the workers, okay? Have a good professional relationship with them so that we can, as workers, we live happily with one another. But also, as a manager, you can solicit valuable information and ideas from your workers, right? So if we do Kaizen, then every day the house is elevated to a higher level of quality and efficiency a little bit, right? And over time, the house will be operated at a very high level of quality and efficiency. And that's the idea here, right? Process improvement. The second foundation is we try to smooth out the flow, right? We try to produce at a relatively constant production rate with little variability. And we should have the built-in flexibility. The built-in flexibility is right there in the fast changeover, right? So that we can deal with a mixed model. And with the mixed models, we can do the smooth flow. Okay, so that's the main idea of what they do at Target. Right? We call it as a TBS house. Let me go back to the whiteboard, and I would like to go into some details of this house. Okay, so we are still at module 6. And the next big topic is a Toyota production system, or TPS, right? To summarize it, we have the Leica's view, the 4Ps model, right? But to be more concrete, we will look at the TPS house. So in the TPS house, right, the goal is is at the roof right here. We try to match supply with demand. So literally, right, it means that we try to make supply equals demand. Let me ask you the following question. If we know that in a day we can sell 1,000 cars, then how many cars would you produce? Right? If we know that we can sell 1,000 cars a day, how many cars should we produce? Okay, I already see some answers already. And that is not meant to be tricky, okay? So 1,000 cars are correct. I ask you that question because I would like everybody to be conscious about that matching supply and demand. We say it as matching supply and demand. It means that we try supply to be equal demand, exactly equal. Because if we produce 1,001 cars, then what to do without extra one car? We need to house it. We need to lock up our inventory right there in that one car, right? It's not good. And if we produce only 999 cars, then we lose the potential revenue of the extra of the one car that we should produce, right? So that's why, from the lean perspective, we try to look at the demand and then meet up exactly with the demand, not more than that, not less than that. And that's why we have the just in time or just enough, right? Okay, so at the bottom of the house, remember we have the two pillars. The roof is a goal, but then to do that, we have to have the foundation, right? We have to do Kaizen, process improvement. We have to reduce variation, and we have to have the flexibility in our system, right? We have the two pillars right here. They are all in a slide. So let me go through some of the details that we have in the house, right? By the way, down here we have the Kaizen, and we should have little variability and flexibility. In terms of Kaizen, it should be at the front line, right? Because the workers know the details more than us, the managers. And that's why, you know what, we all start out as a worker, right? We start out as a worker to know the details, and then later on they will promote us to be the managers. All right, so that's the summary, and now I would like to go to some detailed aspects of these house. The first concept is about the pool system. To understand the pool system, let's talk about the push system a little bit. For example, if you work for retail, right, then they will buy a container of goods, and then they will try to sell out that container of goods. But during the meantime, they will carry a lot of inventory, right? So it is called a push system. Then just imagine in that push system, we're going to see a lot of inventory. So from the loans perspective, we will try to avoid that as much as we can. We don't want to hold on to the inventory because it's going to make us to incur the unnecessary cost of holding inventory, right? So at Toyota, they will do more of the pool system. What does that mean? It means that they only produce something if it is already ordered, or production is led by or initiated by demand. I watched a a video about production at the Ford car factory. In one day, they cranked out more than 1,000 cars, okay? Or 1,000 cars, around that number. And all cars are different. And all cars are already ordered by some customers, either by the dealers or by some customers, okay? So in that case, right, the production just equal exactly the demand. Right. So in that case, they don't have any inventory. They finish a car and then they will ship it out, right? So with that system, then normally we do not see much inventory. But in the pool system, there are two further detailed system called a Kanban pool. It's a little bit kind of specific to Toyota, right? Why we call it as a Kanban pool. And then the other is a make to order. Make to order is easy, right? Somebody ordered the car, we might just produce that car. That's make to order. Kanban pool is sometimes we need these container parts of screws and nuts and bolts. So you draw the whole containers. The containers here are a tote or a box, something like that. It doesn't have to be the big containers, okay? But then when you pull a container apart, then in a sense you do some batching. And batching means you carry onto some inventory, right? So Kanban pool is not as extreme as a make to order, but sometimes it is necessary because you have to carry enough nuts and bolts and screws, right? Otherwise, later on you might have some shortage of those. So in the production process like this, then normally the Kanban pool will be in the early part of it, where you have to carry enough bolts and nuts and other parts, essential parts. So Kanban pool normally happens here. And the make to order will happen here. Right? They only produce a car if it is already ordered by some customer. In the Tesla case, in one weekend, they got the hundred thousands of orders in one weekend, right? Something like that. Then of course they already have the order, and they try to meet up with the order. But the Tesla case is where they don't have the capability to meet up with all of the orders, right? If you order something from Tesla right now, it might take 2 or even more years to get your delivery. So of course, not meeting up with the demand is bad because you don't have the car to deliver. So it means that you do not have the revenue right away. The customer might put some kind of deposit, but the deposit is just a little amount, right? You need to deliver the actual car to get like 30, $40,000, $60,000 or something like that, right? So Tesla will take more time to catch up with the demand. They are building a new factory in Austin, Texas, and also another one in Berlin, possibly another one in China too, right? So that they can meet up with the demand. All right, so that's about the pool system, right? If we use more of the pool system, then we can kind of reduce the inventory, which is the extra inventory or the waste, right? So that's one way to reduce the waste at Toyota, and everybody should learn from that too, right? Another quick concept here is called the U-shaped curve, U-shaped layout. So the U-shaped layout goes as following. We have instead of making the assembly line as a straight line like this, right? Now they bend it to be the U shape like this. And then the station position along the way like this. The workers and the station staying in that U shape. The advantage of doing the U shape is, for example, you bring a cart here, and the same cart can be moved and supply the parts to other parts to the different station of it, right? It's very convenient, it's very time saving, effort saving. You can easily supply the different stations, right? Sometimes the workers, they can easily walk across different stations. If the assembly line is a straight line like this, a worker will have to walk very long before they reach the station that they need, right? But with a U shape now, you can cut that walk time a lot. So the main idea of the U shape is we would have less distance. Less distance means less walking, less time for walking, right? Less time to walk. It is time saving right there. And then less distance and easier supply and support. Sometimes the chief engineers have to inspect different parts of the assembly line. Sometimes they have to jump in and help the workers out, right? So the engineers will not have to walk that long. They will have faster response to the station. All of these are important, right? So it's all about efficiency right here. Okay, so that's a U layout. I would like to move on to the next concept right away. So in the next concept, we learn a new things called the takt time. To do that, I would like to refer you to the example on slide, I think 62. Let me confirm that. Oh, 42. All right. So let's look at let's call this as a factory example. This is module 6, slide 42. Okay, so we have a car factory. It is open for 2 8-hour shifts per day. And the demand rate is 960 cars per day. We do not have enough time, so I only focus on part A of the question. In part A, they ask the following. What is a takt time? Right, so takt time is the word takt itself originated from the German language, and then the Japanese use that, and then I don't know, the word is cut short, and now we have the takt. Okay, otherwise it's going to be a very long word. So takt time is calculated as the following. It is available time divided by the demand rate. All right, so let's put the numbers in. In a day, we have 2 shifts, so 8-hour shift, right? So we take 8 hours, multiply 2 to have how many hours per day? And then the demand rate is 960 cars a day. All right, the day will be canceled out. We only have 16 hours for those 960 cars. Right, so that's a takt time right there. How much time is needed to that we have to produce the demand, right? But then in the current form, it's a little bit hard to grasp the concept. So we convert it to the minutes, 16 times 60 minutes divided by 960 cars, or 960 minutes for 960 cars. So it means that we need to have a takt time of 1 minute per car, right? So what does that mean? It means the following. We can interpret it in the following way. So to meet up with the demand of 960 cars a day, then we need to configure our process so that we can crank out 1 car per minute, right? So to produce a car every 1 minute. I say every 1 minute rather than every minute, because it can be 1.5 minutes, it can be 2 minutes, right? Things like that. So the idea here is to meet that goal, then we need to have this pace of production of 1 minute per car. So that at the end of the day, we have 960 cars done, right? So that's the idea. So the concept behind the takt time is, it is the goal, it is a target, it is a desirable pace of production so that we can meet up with the demand, right? So that's a takt time. At this time, right, I would like to compare the 3 time concepts that we have learned from the beginning of our class. So this is a comparison between the flow time and then the cycle time. And today we learn the takt time, right? How are they different? The first one, or the flow time, we learn it way early on in the semester, right? So the flow time is how long it takes for 1 unit to go from the beginning to the end of the process. So I would like to draw a picture to illustrate the flow time. We all know this. I just want to review it a little bit. So this is our process like this, right? A car will have to go through the door of the factory and emerges at the end of the factory, right? So we call that as a flow time. In modern car manufacturing, it takes about 17 or 18 hours from start to finish, right? The suppliers will bring the part to the front door, they take it in, turn the parts into the complete car. It takes about 17 to 18 hours. Right? We call that as a flow time. The cycle time is different. The cycle time is the time gap between 2 consecutive units. Right. So if we, one more time, I'd like to draw the picture to illustrate it. So we are looking at the same car manufacturing process. Right. Now we're not calculate the time from start to finish. We only measure the time distance between the 2 consecutive cars. So for example, in this case, we have some cars lining up in the factory like this, right? Then the distance between these 2 cars is called the cycle time. Another cycle time right here, another cycle time right here. We already talk about the average cycle time, right? So the and in this case, for example, okay, the cycle time is 2 minutes per car. Then the cycle time tells us what? Every 2 minutes go by, or another car will exit the process. Another car will come in, another car will exit. Another 2 more minutes, another car comes in, another car exits the process. We said that, right? So that's the rhythm of the production process. So this is an actual pace of production. What is going on right now? And for example, the actual pace of production is 2 minutes per car. Okay, so that's the cycle time. The takt time sounds very similar to the cycle time, right? But it is delicately different. So in this case, let's take the example of the takt time as 1 minute per car as our example. Then it sounds like the cycle time, right? It's also how many minutes per car, but it is different. Okay, so the cycle time of 2 minutes per car is what is happening right now, whereas the takt time of 1 minute per car is what we want it to be, right? So let me make the note here. The takt time is the desirable or the target pace of production. Right? We want our process to crank out 1 car every 1 minute, whereas the cycle time is 2 minutes per car. I would like to ask the whole class the following. With that cycle time, with that takt time, do we meet the demand or not? Please feel free to share your thought in the chat window. With that cycle time, with that takt time, do we meet this? Do we meet the demand rate or not? Jaylene, Fallon. Oh, and a lot of you already had Theo. Okay, Michael. Okay, you are all correct. In this case, the 2 minutes per car is too slow. It is what happening right now. And what is happening right now is too slow relative to what we want it to be. What we want it to be is a takt time, right? We want to be 1 minute per car, but we only working at the half the desirable pace, right? So at the end of the day, we have a backlog of orders that we cannot meet. That's not good. So in that case, right, we need to reconfigure the process. So to have a cycle time, to have the actual cycle time 1 minute per car, right? So again, the cycle time and the takt time sounds very close, but they are delicately different. The cycle time is what is happening right now. That's what we can measure. The takt time is calculated. So that's a goal, that's a target. That's what we want it to be, right? So one is actual, the other is desirable. Okay, so I hope you see the difference between the two. Okay, so I would like to end the class here. I would like to see you back on Wednesday. So have a good rest of your day, and thank you for joining me. If you have a quick questions about the checkpoint, then please stay back and ask me.